right. So when we talk about rates of reactions, another important concept to discuss is the idea of equilibrium. So throughout this, we're going to define what equilibrium is, talk about the equilibrium constant, and then the equation that is used to solve for that. So equilibrium occurs when you have what we call a reversible reaction, which means that it's possible for the reaction to go backwards. Or really what happens is that not all of the reactants turn into products. You'll see this, or you'll know you're dealing with an equilibrium reaction when you see the arrow written like this. It's a double-sided arrow that goes forwards and backwards. All right, so that's how you know you're dealing with a reversible reaction and you're dealing with this idea of equilibrium. And what equilibrium means is that there is an ideal ratio of your concentration of your reactants in your products. All right, so that means that there's this amount of products to reactants that just kind of makes the system happy. All right, for example, it could be that this reaction reaches equilibrium when you are at 70% of the molecules have become carbon dioxide and 30% are still carbon monoxide and oxygen. All right. So equilibrium is, you really want to think of it more like balance than per se being equal. All right. So it's very likely that there's going to be more products than there are reactants. It's just there's this value, this ratio of the products to the reactants that causes the reaction to just kind of stop. All right, so the reactants remain, the products remain, and the reaction's done. So I think seeing the equation for this might make this sink in a little bit better. So the equation for the equilibrium constant, all right, also referred to as KEQ. K is a letter that is often used for constants. All right, KEQ is equal to this. I know right now this looks a little bit complicated, but this is written in a format that is very just kind of generic for us. All right, so that we can apply it to any reaction. But really what the equilibrium constant is, it's the ratio or the relationship between the products over the reactants. All right, so your products, the concentration of your products goes over the concentration of your reactants. And so that we can deal with any reaction that we have to deal with whether or not there's, is there 2 moles of carbon monoxide or just 1 mole of carbon monoxide in this particular reaction. So what this base equation means is that the little letters represent things like the coefficients. So like say we were working with this equation. I have to write it out and then I'll balance it. And this, instead of being a reaction that goes to completion, it was a equilibrium reaction. All right. Let's see, I need a 2 here. 1 is fine there, and a 2 here. All right. The little numbers are your coefficients. All right, so we've got nothing in front of CH4, so that's going to be a 1. The big letters are your chemicals, so that's the CH4. And then we've got 2 and O2. And then we've got, again, another 1, and then CO2 is the chemical. And then a 2 and H2O. All right? And that tells us, this helps us plug things into this equation. All right? So whatever represents big D is going to go in this, is the chemical name, and it's the concentration of that chemical, and it's going to be raised to the power of little d. All right? Let's do one. So write this down, that way you have it, and then we're gonna do a few examples as far as setting these up. Okay, so here's a good one. So we've got big A, and then little a is going to be just the invisible one out in front of N2, and then big B is the HCl, and then 6 is going to be the little b. All right, big C is going to be NH3, little c is going to be the 2, and then big D is going to be Cl2, and the 3 will be little d. All right, so that's what that generic equation helps us do. It helps us identify what goes into here. All right, we know our products are always supposed to go on top. So I'm going to plug in for C, I'm going to replace that with NH3. And for little c, I'm going to square this. All right, for D, big D, I'm going to put in Cl2. And then that coefficient, the 3, so we're going to cube that. And that's going to be over let's see, A will be N2. All right, and there's no coefficient, or I can raise it to the power of 1 if, that makes things easier for you to just remember that you should always have an exponent, but multiply or taking something to the power of 1 doesn't change the value. And then B will be HCl to the power of 6. All right, so that's how you take an equation and put it into this equilibrium constant. All right, it's really just identify the parts you have and then plug them into the appropriate spots. So let's do another example. All right, so we've got our A, and our little a is going to be the invisible one. We've got our B, and then here we have C. All right, so just because this format has 4 options, you're going to run into reactions that maybe only have 3, or maybe reactions that have 5 different components. All right, that's where you want to remember worst case scenario. All right, this is always going to be your products over your reactants. All right, you can change the number of parts, but you need to make sure that all the product information goes on top and all the reactant information goes on the bottom. All right, so for example, for this one, I'm not going to have a D component. So all I'm going to have up top is NH3 squared. All right, and then what's the bottom going to look like? You'll have 2 parts. You'll have your N2 to the power of 1. And then what power is the H2 going to go to? That's going to be to the 3rd power. All right? So here's one more. This is one that I know is going to show up on your quiz as well. I want you to try this one on your own first. All right? See if you can come to the correct answer. And then you can start the video back up and see if you got it right. So this one's the opposite of what we had before. We have A, we have 1 reactant, all right, but we don't have the other one. So now I'm going to skip to C and D. All right, so we don't have B. So I'm going to have NO squared times O2 to the 1st power over NO2 squared. All right, so this is something where, again, some of you may pick up on this really, really quickly and like, oh yeah, that makes total sense. Some of you might need more practice, so talk to me if you need that. All right, the last thing I want to cover is, I know you'll have one quiz question that is like this one, where you actually have to plug some numbers in. All right, so we've got our I've actually done this one before. So we have our NH3 squared over N2 times H2 cubed. All right, if you have numbers, now you just take this one step further. Inside these brackets, you're going to plug these numbers in. All right, so you're going to have, let's see, NH3 is 0.02 squared. And then that is going to be divided by, let's see, N2 is 0.04 times 0.07 cubed. All right, so then let's simplify this. 0.02 cubed is going to be 0.04 over 0.04 times 0.000343. All right. Now, my recommendation to you before dividing is simplify the bottom down to one value. So you got your 0.04 divided by, that gives you 0.00001372. Now, plug that into your calculator, and you should get an equilibrium constant of 2.91. All right. So, this is definitely not the difficult part is setting things up. Just plugging in the numbers shouldn't be too bad.